Today we're talking about the second fundamental theorem of calculus, which is really the same as the original fundamental theorem, just looking at it kind of from the opposite perspective. So we're going to start by reviewing what really is the fundamental theorem of calculus. The fundamental theorem of calculus was pretty much how we took integrals in the last unit. As we found an antiderivative for the integrand, we plugged in the upper limit of integration, we plugged in the lower limit of integration, and we subtracted. But I'm going to rewrite this just by adding f of a to both sides in a way that's going to be really useful to us this unit. So I'm going to say that f of b is equal to f of a plus the integral from a to b of f prime of x dx. Which is to say that the end value is given by the starting value plus the accumulation of some rate of change. And this is going to be a really helpful way for us to think about integrals, especially in this unit where we're studying accumulation functions. You can imagine, the rate at which water is dumped into a container. It follows this function. How much water is in the tank at time 10. Other accumulating things. It's very applicable to real life. And so I think before I really go on and give you the second fundamental theorem of calculus, I'm going to kind of give you a reminder about the derivative. So if we've got a function f of x, the derivative is, we know it's the slope of the tangent line. But the actual numeric value of the derivative, okay, so, it's the slope of the tangent line, whatever that means. And I'm sure in Algebra 1 we talked about slope a little bit this way, but, if this is, say, x equals 3, and this is f of 3, then the derivative is being the slope without regard to that's why I made the rest of the graph dotted, because I really don't care about it. The derivative is how much we expect f to increase when we increase x by 1. So that, if I were to, say, zoom in, if I went over 1 unit, I would go up dy dx units. Okay, and this is going to be useful to think about when it comes to actually do the second fundamental theorem, or realize why it works. Now in this unit, we're going to be studying functions defined by an integral. So, maybe I'll say that f of x is some function that's defined by an integral. The integral from 0 to x of some other function, g of t dt. And now we do need to use a different variable for g, but y'all have seen, it really doesn't matter what variable we call it x, we call it t, call it w, it doesn't matter. Okay? We need a dummy variable. And that's something that you will grow more comfortable with over time. And I'm going to sketch a graph of g. All right, there it is. And this is supposed to be a line segment and a semicircle. Okay, so this is the graph of g. Now, I think we should start by actually finding some values of these functions defined by integrals. Okay, and so I'm going to say f of 0. I'll start with an easy one. We may just see what f of 0 is without doing any sort of thinking too hard. It's going to be 0, yeah. Because f of 0 is equal to the integral from 0 up to 0, which is basically where we can stop and say that no matter what we're putting in as our integrand, it's going to come back 0. G of t dt. Okay, maybe I'll consider f of 3. And that's the integral from 0 to 3 of g. And, well, we're going to count the area from 0 up to 3, and that's going to be a rectangle. It'll be basically this area, and it'll be a 3 by 2 rectangle, which is going to be 6. And maybe I could ask about f of 5. Well, f of 5 is the integral from 0 to 5 of g. We can also find using geometry. It's going to be those 6 units plus the area of this semicircle. Now the area of this semicircle is going to be half of the circle that has radius 1. Right? Because the center of the circle would be right here. And it would have radius 1. So that's pi times 1 squared is pi. So I'm going to add pi over 2. So it's going to be 6 plus pi over 2. And that's how we would evaluate functions defined by an integral. And now that I know how to evaluate a function defined by an integral, I could maybe be interested in the derivative of a function defined by an integral. Okay, so again, I'm going to define f of x is equal to the area counting function that starts at 0 and goes up to, x of this g function. And so what I'm going to do is I'm going to actually kind of erase this. And we know that it's a flat line. I'm going to call that 2. It's a flat line. And then it kind of does this. So thinking back to how I had talked about the derivative earlier, if I was to increase x from 2 to 3, how much area would I be expecting to add on my function that is counting area? 2 units. Okay, so right here, I'm expecting to add this much area. And we know that that's actually how much we're adding. So that indicates to me that the derivative of f at x equals 2 is equal to 2. Okay, then I'm going to do the same thing over here, and I'm going to remove the right half of this semicircle. And I'm going to think, okay, if this is x equals 4, how much area am I expecting to add, just based on what I can see here, how much area I'm adding at this moment at x equals 4, how much area am I expecting to add when I move up from 4 to 5? Okay, so yeah, you might think you're expecting to add pi over 4 because you know that the thing is a semicircle. But the derivative, remember, it doesn't care what's happening after the point of tangency. So it's thinking, based on where I am right now, I'm thinking I'm going to be adding 1 unit of area. Okay, just because it's the height of the function. And so I'm going to say that f prime of 4 is equal to 1. And in general, I could say that the derivative of f at some point x is really just the height of the g function, right? How the y value on g. So that's really just g of x. And so what I'm going to do, and you'll see me this a few more times, is I'm just going to say that when we take the derivative, we're going to take that upper bound of integration, that is a variable, and plug it in wherever we see t, or the dummy variable if the dummy variable is not t. Okay, so f prime of x is equal to g of x. Maybe I'll draw a little cloud around this thing to indicate its relative importance. And this is what I'm going to call the second fundamental theorem. Now, I'm going to flip back over to the original fundamental theorem, which pretty much said that there was the connection between the antiderivative and the area under the curve, but it also said that the antiderivative of the derivative is the original function. Whereas the second fundamental theorem says that the derivative of the integral is the original function. So they're really saying the same thing, that there's this reciprocal relationship, this inverse relationship between differentiation and integration. The relationship between the two is going to be, really the core concepts that we are studying in this course. So I think now it's time for us to maybe consider some actual examples. Okay, I lied. I need to actually consider one other case. And I'm going to just give you the full definition. Okay, so if f of x is defined by the integral from some number up to x, and I'm going to aim to show you why it doesn't matter what number it is, it doesn't impact the derivative. So the number from some, or the integral from some number a up to x, g of t dt, then we'll have the fact that f prime of x we get by taking this and plugging it in for t. And so if you're wondering, like, why does this work? Or why does it not matter what the lower bound of integration is? Well, let's just say that g has some antiderivative capital G. Well, we know how to take this integral. We're going to find an antiderivative. We're going to plug in the top, and we're going to plug in the bottom, and we're going to subtract them. Now, remember that g of a is just going to be some number, because a is a number, and we can plug the number into this antiderivative, and we'll get some number back. So when I go to take the derivative, find f prime of x, that's going to be g prime of x, capital G prime of x, minus the derivative of just a number is going to be 0. And the derivative of the antiderivative is just going to be the original. And so we'll see that f prime of x equals g of x. But there is another case that we need to consider. And I'm just going to, at this point, talk about taking the derivative of a function defined by an integral, because then we're going to have too many function letters and it's going to get confusing. So if I want to talk about the derivative of the integral from some number up to some function that's not just x, like x squared or sine x or e to the x, log x, something like that. G of t dt. Well, what we're going to do is, just like before, we're going to take this, we're going to plug it in wherever we see t, which will be, okay, so wherever I'm seeing t, I'm plugging in h of x. But then I do need to multiply by the derivative of h of x for the chain rule. And now we are definitely good and ready to do some examples. Okay, so we'll start with an easy one. Just say, find the derivative question. Okay. So why don't y'all try this? See if you know what you're doing. See if you followed what I was talking about earlier. And just don't forget the chain rule, you know? All right, there you go. So remember that we're just taking that upper bound of integration and we're plugging it in for t, because the derivative of the integral is the integrand. And so on the left, I multiplied by 1 just to remind myself to use the chain rule. And even when we were new to the chain rule, you didn't see me just multiplying by 1 on the outside or anything. But this, it's such a common error to forget to multiply by the derivative when doing a second fundamental theorem problem where the upper bound is not just x, that I'm going to put that 1 there quite often. Okay, the next thing we're going to do is going to be 2014 AB number 3. And you can find this, it's number 6 on your free response packet for this year. Okay, and it's going to tell you that g of x is a function defined by, the integral from -3 up to x of f, where f is the graph pictured over here. Okay, the first part of this question is going to ask you to find g of 3. But I'm actually going to ask you to find more than that. Because I'm extending this question. I'm going to ask you to find g of negative 3. I'm going to ask you to find g of 3. I'm going to ask you to find g of negative 5. Okay, so why don't y'all try that and just see if you're doing it right. If you're watching at home, you should pause the video because it's going to pop up in a few seconds. All right, there you go. So starting with g of negative 3, g of negative 3 is the integral from negative 3 to negative 3 of some function, which is always going to be 0. There's going to be no area. G of 3, we're going to have to count the area starting from here at negative 3 and going all the way up until positive 3. And so we're counting, we get 6 units of area from here, 4 more, that's 10. But then we ended up losing 1, and so that's 9 total units of area, which is why g of 3 equals 9. Then g of negative 5 is we're going to count the area from negative 3 to negative 5, which is counting backwards. Okay, so it's going to be the opposite of, what we'd expect. So it's the area is 2 of that triangle, so g of negative 5 needs to be negative 2. Okay, the next thing I'm going to ask you about is, they're not asking you this question on the actual free response question, but, this is a natural next question, is what's the value of the derivative of g at these various x points? And so one of the things that they're looking for on the free response section on this type of question is they're looking for you to tell them very clearly that you know what the derivative of g is at any part throughout the question. That's oftentimes one of the points, is states that g prime of x equals whatever it is. So what is g prime of x in this case? Yes, f of x. Okay, so I'm going to say that this is f of x. Okay, and that's going to be, really important for us to state very clearly. You don't really have to state it more than once, but show the reader you know what the derivative of g is. So when I say that g prime is, I'm looking for g prime of 0, really what I'm looking for is f of 0. And I can find f of 0 by looking at the graph. F of 0 is the y value where x equals 0, and that's 4. G prime of 2, that's f of 2. Okay. And that's going to be right here, that's going to be 0. And g prime of negative 5, that's f of negative 5, which is 2. So that's just finding values of the derivative.
In this case, there's no chain rule implications because it's just x.
Yes, exactly. If this had been from negative 3 to x squared, this would become a very different problem. But you'll see that the later parts of this question add their own type of intrigue that doesn't really get that. Okay. Okay, so what if I asked for g double prime of negative 1? What's g double prime of x? F prime of x, because if g prime is equal to f, I take the derivative of both sides of that equation, I'm going to get g double prime equals f prime. So I'm actually going to write that down. Okay, and then g double prime of negative 1 is going to be f prime of negative 1, which is the slope of f at x equals negative 1. So if that's right here, and we can calculate that using rise over run. And so going from negative 3 to 0, I rose by 4 when the x increased by 3. So I'll say that the derivative of f at negative 1, which is also the second derivative of g at negative 1, is positive 4/3. The second question they actually asked on the free response question was, where is g increasing and concave down? Well, I'm going to recommend that you kind of unpackage that question. Okay, so I'm going to say that g increasing is equivalent to g prime of x is positive, which means that f of x is positive. And now that's happening for all x from -5 up to +2. Maybe excluding -3 if that's how you felt. But I'm going to just kind of label that over here. And then if they asked for where g was concave down, we know that that means that g double prime of x is negative, meaning that f prime of x is negative. Okay, now we're looking for where f is decreasing. Okay, well, I'm seeing f is decreasing from -5 to -3, and from 0 up to 4. I think this problem came with some sort of disclaimer that the domain of f was -5 to +4, or something like that. We don't really need to worry about that. And so if we're looking for where g is both increasing and concave down, well, we're looking for the overlap of these two regions. So that's going to be here and there. And that's giving me x is between -5 and -3. Also from 0 to 2. Okay, so when you're, I mean, this is a very common type of question. It's almost like the question, the whole first half of some quiz out there is modeled off of this exact one question, it seems like. And so that's where this is all coming from. So that's my recommendation. When you're asked for something like that, unpackage each statement, get it in terms of f, look at the graph, and then draw your conclusion. Okay, next it's defining some function h by g of x divided by 5x, and find h prime of 3. Well, in order to find h prime of 3, first we need to find h prime of x. We're going to use the quotient rule. Okay, so that's bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. All right, but we know that g prime of x is equal to f of x, so that's going to be something I'm going to just replace. Right? And so h prime of, is it 3? Yeah. Is going to be 15 times f of 3. Well, f of 3 is, looks like down here, that's looking like -2. Minus g of 3. Now the thing is, we calculated g of 3 in part A of this question. I don't remember what it was though. Was it 9? Okay, yeah, it was 9. Okay. Yeah, times minus the top times the derivative of the bottom. Thank you. 141. Okay, so g of x was 9, saved me just in time. This is 5 divided by 5 times 3 is 15 squared. Okay, maybe you know that 15 squared is 225, but I'm still recommending that you write it like that. Right? A lot of y'all made arithmetic errors on the test on an integral after you had already had the correct answer. And that's really sad because that costs you half a question in this class. And it could, on the free response section, cost you the whole point of the answer. You know, and that's really sad. Okay, so we're going to stop here and not risk the arithmetic, right? There's enough errors to be made on this already. You know, maybe you forget to take the derivative of 5x when you're doing the quotient rule. That'll ruin your answer. And so you don't need arithmetic to ruin your answer too. Okay, the next question I'm going to ask is, write the tangent, write an equation for the line tangent to the graph of g at x equals 1. Well, we're going to need a point. It's going to be 1 g of 1. And I don't think we actually found the value of g of 1. So I'm going to do that. And no, we did. G of 1 is 9. Oh, no, that was in yesterday's section. I found that. But what happens is, over here, this is a positive 1, making this 3. And so it ends up being 9 all the same because of the symmetry of the graph. Okay, so g of 1 equals 9. The slope is g prime of 1 equals f of 1, which is 2. So the equation is y minus 9 is equal to 2 times x minus 1. All right, I'm changing part D a little bit so that it's more interesting to what we're doing today. And I'm going to say let p of x equal g of x squared minus x and find p prime of x. All right, well, I'm going to actually write an equation for p of x. Remember that g is the integral from -3 to x. So wherever I see x in the formula for g, I'm replacing it with x squared minus x. So this is from -3 up to x squared minus x of f of t dt. And then when I go to take the derivative, I'm going to remember to take this and plug it in wherever I see t. And then I'm not going to forget the chain rule. Okay, so this is f of x squared minus x times 2x minus 1. Now, I would recommend, if you're going to do these free response problems to help you study, I would recommend doing part D as it was requested initially. But as for what we're doing today, this is more interesting. What is the maximum value of g of x on the closed interval -5 to 4? This is an absolute maximum question, the maximum on a closed interval. So we're going to do the closed interval test, or the candidates test. I'm going to set up for that. I'm going to set up my little table, the x values I'm interested in, and then I'm going to evaluate g of x at each of those. Now, the x values I'm interested in are the endpoints and the critical points. Now, the critical points are where g prime either equals 0 or is undefined. G prime is f of x, so I'm looking for where f is equal to 0. And that's going to give me x equals -3 and x equals 2. Okay, now I've already done a few of these in the work that we've done on this problem already in part A, I think. We found g of -5, that was -2. We found g of -3, that was 0. So now all that's left is for us to find g of 2 and g of 4. Did we find g of 2 in this section? I feel like I might have. No. Okay. Yeah, okay, it's going to be 10 because I'm starting at -3 and I'm counting area all the way up to x equals 2. And that'll be 6 plus 3 plus 1 is 10. So like that. And then g of 4, well, I'm going to have to add some more area in. But if this is 3 and 1, this is going to be -1 and -3 just by the symmetry of this line across its 0. Okay, so it's going to be 6 plus 4 minus 4 is just going to be 6. So then I conclude that the maximum value of g on the interval is right there. And the value of g is this. It's the y value, not the x value. So I'll say the maximum value of g on the interval -5 to 4 is 10. Okay, that's the missing piece. I've asked you questions about derivatives. I've asked you questions about integrals. What are we missing? A limit question. Okay, so find the limit as x approaches 0 of g of x minus 6 divided by x. What is my first recourse when encountering a limit question? Just plug it in. Okay, so maybe we'll be lucky, and this time it won't come back 0 over 0. Okay, so this is going towards g of 0 minus 6 divided by 0. Oh, that doesn't look good. And so g of 0 is 6. 6 minus, okay, so this is 0 over 0. So what am I going to use? L'Hopital's rule. Okay, so I'm going to use, yes, L hospital rule. All right, so I'm going to use L'Hopital's rule, where this is going to become equal to the limit as x approaches 0 of the derivative of the top, which is g prime of x minus 0, divided by the derivative of the bottom, which is the derivative of x, just 1. Okay, now I'm going to try again. Well, g prime of x is equal to f of x. I know that. So this is going to be f of 0 divided by 1. F of 0 is 4. So that's going to be the value. Okay, so we can ask L'Hopital rule questions with functions defined by an integral. And I'll tell you, just a piece of advice, if you ever see a limit question where there's an integral in either the top or the bottom of the fraction, it's going to be a L'Hopital's rule question. That's one I've been seeing quite a bit the past couple of years. I've been looking closer, but I've kind of run into a few of them. And the question was, do we still need to show that it goes to 0 over 0? Absolutely. We need to show that it's going to 0 over 0 or infinity over infinity, and we need to state explicitly that we're using L'Hopital's rule. Okay, now we're given the picture of a graph of some function, and we're going to define f to be the integral from 0 up to x of that function. So the first thing we need to do is show the reader that we know what the derivative of f is. So I'm going to explicitly say that f prime of x, so I'm taking this, I'm plugging it in for t, and I'm not forgetting the chain rule. So this is g of x multiplied by 1. Okay, and I'll just get rid of that. So f prime of x equals g of x. All right. So now we're going to ask kind of these maximum, minimum, increasing, decreasing, concave up, concave down questions. All right, so where does G have a relative maximum or a minimum? I know when we did that question on the free response about increasing concave down, I encouraged you to unpackage that statement. Okay, so I'm going to do that. We're going to say, well, G has a relative maximum or minimum wherever G prime has a sign change. And we know that G prime is F. Or no, F prime. And that's why I switched it, is because, you don't want to get too stuck with F being the integral of G or G being the integral of F. So where does F have a relative max or min? Wherever F prime has a sign change, which is where G has a sign change. All right, now, I'm going to say, well, G has a sign change at B, and G goes from positive to negative, which means F prime goes from positive to negative, meaning F goes from increasing to decreasing, which is a relative maximum. And then at x equals D, okay, G is going from negative to positive, meaning F prime is going from negative to positive, meaning F is going from decreasing to increasing, which is a relative minimum. Next, I'm asking, where does F have a point of inflection? We know that a point of inflection is a sign change in the second derivative. Okay, so F double prime has a sign change when, well, we don't have an equation for F double prime, but we can see that if F prime is G, F double prime will be G prime. So G prime has a sign change, meaning that G is going from increasing to decreasing or decreasing to increasing. What x values are you seeing that satisfy a sign change in G prime? Yeah, A and C. Okay, so I'm going to say x equals A and x equals C. Okay, if I were to ask, where is F decreasing? Well, wherever F prime is negative. No, that's what decreasing means, is that the derivative is negative. So F prime is negative. That gives me that G is negative. Okay, and we know that G is negative wherever the graph is below the x-axis. And so that looks like between B and D. So I'll say B is less than X is less than D. If they ask where F is concave down, I think I'm going to have y'all kind of look at that. Try it on your own. and see if you're doing it. See if you know what you're doing. Any issues with this? All right. Okay, so I said that it's concave down when its second derivative is negative. I know that the second derivative of f is going to be given by g prime. And if g prime is negative, that means that g is decreasing. And we see that g is decreasing from, kind of up here where it's at its maximum to down here where it's at its minimum. So that's from A to C. All right, so we're going to define a function, capital F, by the integral from 14 up to x squared of t minus 100 dt. They're going to ask you where is f increasing. Okay, we know that increasing means that the derivative is positive. So wherever f prime is greater than 0, but we're going to need an equation for f prime. Okay, so f prime, what I'm going to take this, I'm going to plug it in wherever I see t, and I'm not going to forget the chain rule. Okay, so that's going to be x squared minus 100 multiplied by the derivative of x squared, which is 2x. Then I'm going to factor this thing, because that's going to be helpful. So it's going to be 2x times x plus 10 times x minus 10. And then I'm going to be interested in where this is greater than 0. Okay, so I'm going to draw a sketch. If you like to make a number line, go for that. Okay, it's whatever you like. It's the same thing. Okay, but I know this is a third degree polynomial with a positive leading coefficient, and 0 is at negative 10, 0, and positive 10. And I know what a third degree polynomial with a positive leading coefficient looks like. It's going to come from below. It's going to kind of do its thing. Since these are all single roots, they're all passing through confidently. And I can see where this is positive pretty easily. I'm going to say that it's positive through here and over here as well. So that's from negative 10 up to 0, also from 10 to infinity. All right, here we have two more kind of standard take the derivative questions. And so the first one, I feel like y'all could maybe even do mentally. So I'll freeze it and y'all just think about what you would expect the answer to be and then see if you're ready. Okay, so I know what the derivative of 2x is. I know now how to take the derivative of a function defined by an integral. I'm going to take that upper bound, I'm going to plug it in for t, and then I'm going to not forget the chain rule. And I get 2 minus f of x. Now h of x, this is one that we haven't seen yet. This is one that I forgot to show them last year, and then they were all very, very concerned at some point along the way when they ran into one. What do I do with this? You don't just, it's not e to the 5 plus 5, that's for sure. Okay. And so what we're going to do is we're going to rewrite h of x by switching the bounds of integration. And that's going to now become the negative integral from 5 to x to the 4th of e to the t plus t dt. And then I'm going to take the derivative by saying, okay, it's going to be the negative of, take this x to the 4th, plug it in wherever you see t, and don't forget about the chain rule. So that's e to the x to the 4th plus x to the 4th. Then we're going to multiply by the derivative of x to the fourth, which is 4x to the third. If you wanted to rewrite that, you could, but it would be the exact same thing. All right, the last problem I've got for you today is something that we hadn't been able to do in the past, right? There was no, I told you there's no closed form antiderivative for cosine of x squared or e to the x squared or many other functions. Okay. This one, okay, well, we can't write a closed form antiderivative for it, but we could define a function with an integral that would be an antiderivative for cosine of x squared, because when we take the derivative, we would get cosine of x squared. All right, so let's kind of cook one of those up. I'm going to say that f of x is the integral from some number up to x of cosine of, it's going to be squared, so I'll just use t as the dummy variable, dt. Now, what should the lower bound be? Yeah, it could be, you could put anything you like. And so we know that an antiderivative for a function is a class of functions that has like a plus c, right? And so that's really where we're going from there, is that the lower bound is basically dictating which antiderivative, which plus c you're using. So we could call it 0, we could call it 8, we could call it 18, we could call it 187, you know, like whatever you like. These are all antiderivatives for cosine of x squared. And we know that there's not just one antiderivative for a given function. Antiderivative is a class of functions. So I think that's all I got for y'all today. Point one.